Give me 1 second. Uh, yes, okay. We'll start. Right. Now this time, now please highlight that isolated highlight. I will explain why all the time, all the previous examples. So when we were finding intensities at a point due to a given charge distribution, why we always considered isolated. Why it is important to consider isolated charge distribution. I will explain the reason. Right. And please highlight isolated, uh, infinitely long, thin, conductive. Infinitely long, thin, conductive. Highlight those words. Different colors. Highlight. Right. Now this mentioned there is a wire. It's conductive wire that is very thin. Its length is infinitely large. Length is very large. What do you think about the charge distribution? Acting on a very thin, infinitely long conductive wire. What do you think about the charge distribution? Raise your hand, someone if you say, so the charge distribution might be a linear charge distribution answer. As per my understanding, the charge distribution must be a kind of linear charge distribution answer. It must be a area charge distribution answer. Area charge distribution answer. Area. I feel that it should be a kind of volume charge distribution answer. Volume charge distribution answer. Since it's a length, now very clear that thin means it's very thin, length is infinite long. Then from that we can come to a conclusion. Its length is significant than the other dimensions. So therefore remember the charge distribution on the very thin, infinite long conductive wire is going to be a linear charge distribution. It's going to be a linear charge distribution. Right. Then, okay, I'll draw that wire. If I do the wire, if I do the wire, okay. If I repeat the heading again, the heading is around isolated, comma, charged, comma, infinitely long, infinitely long, thin conductive wire, thin conductive wire, thin conductive wire. Right. Look at this sub story. I draw the wire like this. The length is infinitely long. To show that its length is infinitely long, I use some dotted lines in both ends of the wire. Then you understand the length is infinitely long. Right, okay. That's okay. And let's say the wire is positively charged. Let's say the wire is positively charged. It's a positively charged wire. And they have given the charge density, linear charge density given as lambda. Right. Given data, linear charge density of this wire is lambda. Lambda. Right. Given data, linear charge density. That is lambda. Now already we know what does it mean by linear charge density, right? I think you can remember the story. This wire is a very long wire. Now what's my target? So now you are going to find the intensity at a point. My question is exactly which point are you going to take your intensity? Now I'm going to find the intensity at a point. I want to find the intensity at a point. Let's say simple r distance far from the conductive wire, perpendicular to conductive wire. I'm going to find the intensity at a point, a simple r distance far and perpendicular to my conductive wire. In that case, let's say, now I want to find intensity at a point which is simple r distance far from the wire and perpendicular to the wire. This is my point capital A. My target is finding intensity at point capital A, the distance, simple r distance, perpendicular to conductive wire. So then what we have to do is, what we do normally is, we want to apply Gaussian theory. Then step one is, first of all, identify the charge distribution. Yes, I identified the charge distribution is a kind of linear charge distribution. Second one is identify the distribution of electric field lines. You want to understand how the electric field lines have spread through this wire. Identify the distribution of electric field lines. Third step is select the Gaussian surface. Select the Gaussian surface. I told you that when you are selecting the Gaussian surface, the first thing is the point which you are going to find the electric field intensity must be on the Gaussian surface. The second condition is the Gaussian surface must be perpendicular to the electric field lines coming from, if it's spreading from the object, right? If you can decide these three, the remaining story is very simple. Now just think this is your very thin wire. So we will know that. Just consider a point. Look here, I consider this perimeter of this wire. If I consider this perimeter of the wire, we all know that electric field lines are leaving from the wire perpendicular to the wire, all the directions. Likewise, if I ask you, right, when you consider the wire, if you consider this perimeter of the wire, right, if you consider this perimeter of the wire, I just enlarge it. I just zoom the perimeter of the wire. It's a very thin wire. If I zoom the perimeter of the wire and if you mark the electric field lines, this electric field lines spread in all the directions. I think imagine the 3D manner. Likewise, if I start drawing electric field line distribution for each and every point on this wire, I think now you can imagine, right, how would be the electric field line distribution, right? Do you understand? So now what can I do now? What can I do if I consider the side view, when someone is looking from the side? If I have a side view of this wire, if I see the side view, if I look at the wire from side view, then what we can see is we can see the wire as a kind of small point. If you're looking from the side, we can see the wire as a small, thin, very small point, the side view. If as a side view, you can see the wire as a very small, thin point. This is how you this is how you are looking the wire. This is how you see the wire. Then if I draw the electric field lines that you can see when you keep your eye from the side, and when you see the wire, this is how you see your electric field lines. Am I correct? If I'm wrong, tell me. If you don't understand, ask. Am I correct? This is how you see your electric field lines. Here is your very thin wire, side view. Now let's say the front view. Now this is your thin wire. If you're looking from front, how would appear the front views? As I mentioned, every point on this wire, electric field lines are distributing. If I draw the front view of this wire, if I do the front view of this wire, the electric field lines spread in this way. Electric field lines leaving the wire perpendicularly. If I do the front view, the front view, electric field lines leaving perpendicularly. If I do the front view, am I correct? I hope you understand what I'm doing. I draw the charges in different color. Then we can identify easily. I do the charges, positive charges on the wire using red color. The charges, right? The charges. Now my target is to find the electric field intensity at point capital A. Before finding that, you should know what is your charge distribution. That is a linear charge distribution. Second one is how the way that electric field lines are distributed. Now we have a kind of idea. We have a kind of idea. Now what can you say about the Gaussian surface? What would be the shape of your Gaussian surface? Any idea? What would be the shape of your Gaussian surface? Just tell some replies. Give me some replies. What would be the shape of your Gaussian surface? So you want to understand at the end of this wire, at every point, electric field lines are distributing in all the directions, right? Electric field lines distributing in all the directions. So if I take a kind of a circle perpendicular to this wire, then you want to understand electric field lines are distributing all the directions. Just tell me, what would be the shape of the Gaussian surface? Give some replies. Now you have to select the Gaussian surface. Obviously, you have to select the Gaussian surface. The first condition is the Gaussian surface must be perpendicular to the electric field lines. Then you know how the way electric field lines are spreading from this wire. The next condition is the point that you're going to find the electric field intensity must be on the Gaussian surface. By satisfying both the conditions, the surface must be perpendicular to the electric field lines. Point capital A must be on the Gaussian surface. What would be the shape of your Gaussian surface? Reply. Give some replies. What would be the shape of the Gaussian surface? We want some of you is telling circle, but remember it should be a cylindrical Gaussian surface. It should be a cylindrical Gaussian surface, right? The Gaussian surface must be a cylindrical Gaussian surface. If I do the Gaussian surface, my Gaussian surface, look here, point capital A must be on the Gaussian surface, and the Gaussian surface must be cylindrical Gaussian surface. Cylindrical Gaussian surface should be cylindrical. Just think why it should be cylindrical. Why it should be cylindrical? Just think. Just try to think. Because you remember, see, if this is a wire, electric field lines are leaving this wire perpendicular to the wire in all directions. So then the surface must be perpendicular to all the electric field lines emitting from this wire. So therefore, in order to achieve that condition, your Gaussian surface must be a kind of cylindrical Gaussian surface. Thereafter, I think you should be able to find the answer. Then you might have a problem, sir. Okay, sir. Now, okay, step one is find the charge distribution. There is a linear charge distribution. Second step is try to understand how the field lines have distributed. That is also done. Then select your Gaussian surface. My Gaussian surface is going to be a cylindrical Gaussian surface. That is also done. Step number four. Step number four is find the total charge inside the Gaussian surface. How am I going to find the total charge inside the Gaussian surface? How am I going to find the total charge inside the Gaussian surface? Sir, you have given the linear charge density as lambda. That's okay. But the problem is, sir, you told us in the beginning, this conductive wire is infinitely long. We know the equation. Linear charge distribution means total charge divided by the total length. Total length. But the problem is, since the wire has a infinite long length is infinity, sir. In that case, I am getting the total charge on the wire as infinite, sir. Remember, they have given the linear charge density as a data. Remember here, we are going to find the total charge inside your Gaussian surface. Total charge inside the Gaussian surface means whatever the length of your Gaussian surface, right? You're going to define it. Let's say now I'm going to define, because even though the wire has an infinite long length, I selected a Gaussian surface having a length less than infinity. This is the Gaussian length. Wire length is so large, so it goes to infinity. But my Gaussian surface then is a limited value. What you can do, you can define your own length for your Gaussian surface. One can define, so length of my Gaussian surface is simple L. Length of the cylinder is simple L. It's up to you. So let's define for L dash something. Length of the Gaussian surface is L dash. L dash. Done. L dash. See, the electric field lines are perpendicular to the Gaussian surface. Electric field lines are perpendicular to the Gaussian surface. L dash. Right. Then so I can find linear charge density is a given data. Then the length of the wire inside the Gaussian surface is simple L dash. Then I can find the total charge inside my Gaussian surface going to be, sir, lambda equals capital Q over L dash. So when I substitute capital Q going to be lambda L dash. Okay, this is the total charge inside the Gaussian surface. Answer, the story is clear answer. Lambda L dash, sorry, the total charge inside the Gaussian surface is lambda L dash answer. The story is clear. The story is clear. Then what we can do, then the last step is apply the equation. If you apply the equation, intensity into area, total charge inside the Gaussian surface over the permeability of the medium. My target is finding the intensity at a point simple r distance perpendicular to the thin wire. Point capital A is here. I want to find the intensity at point capital A. Then if you substitute intensity E, capital A means what? Gaussian surface area. Capital A means Gaussian surface area. My Gaussian surface is a cylinder. Then capital A means cylindrical area. Always we learned how do we find the surface area of cylinder. If you can remember, a cylinder having a radius simple r and a height simple h. For height I say L something. The surface area, the curved surface area of the cylinder can be given by 2 pi RL. You learned 2 pi RL equation, right? This equation gives the surface area, curved surface area of the cylinder. Same story here. Here area means again 2 pi. The radius is the length to point capital A from the conductive wire. This is simple r. Am I correct? Then 2 pi r over 2 pi r into the length of the Gaussian cylinder is L dash must be equal to total charge. That is going to be lambda L dash over permittivity of the medium is sigma. When it's up to intensity, you can get the answer. Capital E going to be equal to how much? Capital E going to be equal to, finally, L dash cancel out. L dash cancel out. Then we can write down lambda over 2 pi r epsilon. 2 pi r epsilon. Right? Correct, right? That's the way of finding intensity at a point. Capital A. Lambda over 2 pi r epsilon. Then what you can do, you can draw this as you are in a side view, and if I mark this Gaussian surface, Gaussian cylinder on the side view, the Gaussian surface going to look like a circle. Am I correct? When you look from the side, when you look at the side, this is going to be a Gaussian surface. Gaussian surface. Surface. Once you finish writing, raise your hands. If you finish writing, raise your hands. The likewise, again, shall we find the variation of electric field intensity with the distance measured from the wire? Now, what I'm doing, I'm just now this wire is placed horizontally. If I place the wire vertically, if I slant the wire vertically, and then how would be the electric field intensity vary along the distance? I'm going to mark. I'm going to mark. So you guys write down the variation of electric field intensity with the distance. The variation of electric field intensity with the distance. This is the wire. Infinite long wire. And this wire is positively charged. Then you are then the y-axis is going to be electric field intensity, and the x-axis is going to be the distance measured from the wire. Distance measured from the wire. Simple R. Now let's consider a point. Let's consider a distance. Let's say now I'm going to consider points which are perpendicular to the wire along this line. Let's say this point as point capital A and point capital B, point capital C something. Point capital C something for our understanding. Then we understand that remember, when you keep a positive charge, now I want to find the direction of electric field intensity at point capital E. This is positively charged. When you keep a +1 coulomb at point capital E, the electric force going to be to the right side. Therefore, intensity, electric field intensity at point capital E also to the right side. And also, remember, intensity, now lambda is a constant. 2 pi epsilon constant. Then you can say that electric field intensity, you can tell that electric field intensity inversely proportional to the distance measured from the wire. The perpendicular distance from the wire. Larger the distance, if not when the point is far from the wire, larger the distance, your electric field intensity going to be lesser. Your electric field intensity going to be lesser. Going to be lesser. Then when you go far from this wire, electric field intensity decreases. When you go far from the wire, electric field intensity decreases. Electric field intensity decreases. When you go far from the wire, electric field intensity decreases. Electric field intensity decreases. Same story. If you keep a positive charge to the right side, left side, electric field intensity going to be what? Electric field intensity going to be direction going to be, now this is already positive charged. When you bring plus 1 coulomb here, positive means there will be repulsive forces acting at this point. Then the electric field intensity direction going to be to the left side. So now we can get the idea. Now we can get the idea. If we get this idea, right. Now we can get the idea, and now we know how to draw the graph. We all know that right side direction vectors are positive. When simple r increases, a positive intensity decreases. Positive intensity decreases. Next one is when you are going to the left side direction. Left side direction intensities are negative intensities. When you go to the left, what will happen? Negative intensities decreases. Negative intensity decreasing. Negative value decreasing. Negative value decreasing. The graph would be like this. Clear. This graph should be the same size somewhat. Right. Answer the story. This idea is very clear answer. This idea is very clear answer. This idea is clear answer. This idea is clear. Then once you finish writing, next idea. The next, once you finish writing the story, we'll go to the next example. Around isolated comma, write down around isolated comma, charged, infinitely long, around isolated, charged, infinitely long, hollow conductive cylinder, hollow conductive cylinder, hollow conductive cylinder. Okay, right. Then write down. Okay, right. Hollow conductive cylinder. As I already explained that when you consider conductors under electrostatic conditions, remember the charges. When you give charge to a conductive, when you give a charge to a conductive material under electrostatic conditions, remember those charges always, if not those charges always place on the surface, external surface of the conductor. Under electrostatic conditions, remember when you provide charges, all the charges will distribute, if not place on the outer surface of the conductor. Now this time we are talking about hollow conductive cylinder. Last day we talked about hollow conductive sphere and solid non-conductive sphere. Now today we are talking about hollow conductive sphere and solid non-conductive sphere story. Now we are talking about hollow conductive sphere. Hollow conductive sphere. Again same story almost. There is a cylinder. Hollow conductive cylinder. Right. Okay. And if I do the axis of the cylinder passing through the center of the cylinder is the axis. You want to think 3D manner. If not, it's not easy to understand what I'm doing. This is the axis passing through the cylinder. Right? Okay. And then you want to understand, since it's a conductor and charges won't accumulate inside the conductor, all charges will distribute along the outer surface of the conductor. When you give a charge, they all distribute on the outer surface of the conductor. Now remember here, this is a kind of 2D drawing that I'm drawing. It's a 2D drawing that I'm drawing. These charges are stored on the outer surface of the conductive cylinder. It's a hollow conductive cylinder. Remember, it's a hollow conductive cylinder. There's a hollow inside. Right. Then what? Then, right. Okay, then, now I want to find the, they have given, now please tell me, first of all, tell me, what type of distribution is this? Raise your answer, the charge distribution is linear charge distribution answer. It's linear answer, linear. It should be area charge distribution answer, area charge distribution answer. It's area charge distribution. Right, okay. So they have given the area charge distribution as how much? That is given as, they have given data. Given data, area charge distribution given as how much? That is given as sigma. They have given sigma. Write down area charge distribution is sigma. Right. Right. Area charge distribution sigma. So the area charge density sigma. Density sigma. Last I explained what is area charge distribution means. Okay. Right. Then shall we draw some electric field lines for our understanding? If not, shall I draw electric field lines separately? So we don't need to mesh this diagram. We'll draw the electric field lines separately. Right? How would be the electric field lines passing from this hollow conductive cylinder? If I do the electric field lines here, look here. Very simple. If I have the electric field lines. So this is the front view. The front view would be when electric field lines are leaving from the object perpendicular to the, since it's positively charged, electric field lines are leaving perpendicular to this object. If I do the electric field lines, this is how electric field lines appear. Am I correct? If I do the side view, if I'm looking from the side, the side view going to be, we know since the conductor, electric field lines won't exist inside the conductor. Since the conductor. If for the side view, we all know the side view going to be side view. When you're looking from the side, you can see the hollow conductive sphere as a kind of circular shape, like a circle. Is your hollow conductive cylinder appears, electric field lines are leaving perpendicular to the, this is your charge distribution. The charge distribution. It's a kind of area charge distribution. If you draw the electric field lines leaving from this hollow conductive sphere, that's going to be, you want to think 3D manner, then only will understand. Leaving perpendicularly. Leaving perpendicularly. The leaving perpendicularly. Right? Should mention this perpendicular mark. Right. Hands up now, this idea is very clear. Hands up. This story is very clear up now. Everything is clear. Hands up. Everything is fine. No issues. Write on everything. If you feel something is important, just write down. So don't wait until I say something. If you feel something important, you just keep on writing. Then okay, right. So then okay. Now my target is to find the intensities at different points inside the conductive cylinder, if not on the outer surface of the conductive cylinder. If not, if I can select a point which is far from the hollow conductive cylinder, how would be the electric field intensity going to vary? Right? That story. First of all, shall we find the electric field intensity at a point inside the conductive cylinder? We find the electric field intensity at a point inside the conductive cylinder. Right. Let's say I want to find the intensity point capital A. This point capital A is a simple R capital A distance, different R1 distance far from the axis of the cylinder. It's simple R distance far from the axis of the cylinder. I want to find the intensity at this point capital A. Then same story, select a Gaussian surface. Two conditions are there. Gaussian surface, your point must be on the Gaussian surface. Gaussian surface must be perpendicular to the electric field lines. Since inside the cylinder there are no any electric field lines, you can select whatever the shape of the Gaussian surface you prefer. Normally what we do, we consider in this scenario a cylindrical Gaussian surface. In this scenario we consider cylindrical Gaussian surface. If I select a cylindrical Gaussian surface, right, a Gaussian cylinder of radius simple Rn, you can define the length that you prefer. If I select a length, let's say that is L1 something, length is L1, the radius R1, length I take it as L1, length is L1. This length is going to be L1. My Gaussian cylinder length is going to be L1. Right? Okay. Right. This is R1. Length of the Gaussian cylinder going to be L1. L1. Right. Then if I consider a point inside the hollow conductor cylinder, shall we find the electric field intensity? Then at point capital A. At point capital A, find the total charge inside your Gaussian surface. Inside this Gaussian cylinder of radius R1 and length L1, there are no any charges inside the Gaussian cylinder, Gaussian surface. Therefore, sigma q must be 0. The last step, apply the equation, intensity into area must be equal to q o epsilon. Then the area going to be the surface area of the Gaussian surface. It's a cylindrical Gaussian surface is a cylindrical Right. Now tell me everything is fine. Everything is okay. Your reply. Everything is okay. Now okay, right? Okay. Right. Okay. Okay. Then I was talking about. Now I wanted to find the electric field intensity at a point inside this hollow conductive cylinder. Then point capital A. I took a Gaussian surface that is a cylindrical surface of radius R1 and length of my Gaussian surface is L1. Gaussian cylinder is L1. Then the total charge inside the Gaussian cylinder was 0. And when I apply the equation, intensity into area equals total charge over the permittivity. Now find capital E. Find capital E. Look at write down capital E. Capital E. The area of the Gaussian cylinder, Gaussian surface. The cylindrical Gaussian surface 2 pi R1 L1. 2 pi R1 L1 must be equal to total charge inside the Gaussian surface, that is 0 over permittivity of the medium is epsilon. And then when you subject capital E going to be 0. Then we realize that if it is a conductive hollow cylinder, any point inside the conductive hollow cylinder, electric field intensity going to be 0. Right? Any point inside the hollow conductive cylinder, electric field intensity going to be 0. That is an important result. Right? Going to be 0. So then, okay, right? It doesn't matter whatever the point inside the cylinder, electric field intensity going to be 0. Now, next my target is I'm going to find the electric field intensity at a point just outside the hollow conductor cylinder. Just outside the hollow conductor cylinder. Then I'm going to select a Gaussian surface. That is also again going to be a kind of cylinder. Gaussian surface is going to be kind of cylinder. Just outside. This is just outside. The radius almost equal to the radius of the Gaussian, the radius of the cylinder. Radius of the Gaussian surface is going to be almost the radius of the cylinder. Thing like that. Red color one is my Gaussian surface. That is also again a Gaussian cylinder. Right. Then let's say the radius of the hollow conductor cylinder is capital R. The radius of the hollow conductor cylinder is it's a simple R. For capital R. The radius of the hollow conductor cylinder is capital R. This is capital R. This red color Gaussian surface is just outside the cylinder. You have to remember radius of the red color Gaussian cylinder also just considered as capital R. I just drew such a way to I drew. It shows that kind of a gap between the hollow conductor cylinder and the Gaussian surface to make us understand to see this diagram clearly. But remember, this red color Gaussian surface is just outside the hollow conductor cylinder. It is just outside, just outside. Therefore, radius of the Gaussian cylinder is also going to be capital R. Radius of the Gaussian cylinder also going to be capital R. Capital R. You can decide the length of the Gaussian cylinder is going to be, you can take it as L dash or L2 or whatever. It is going to be L1, L2, L dash or whatever. L dash something. If not L1, L2 something. L2. Right. Then, shall we find the electric field intensity? Now, let's say my point capital B is somewhere here. I want to find the electric field intensity at a point capital B that is just outside the hollow conductive cylinder. At point capital B. at point capital B, shall we find the total charge inside the Gaussian surface? Then we know that the total charge inside the Gaussian surface in the sense that is equal to the total charge on the surface of the hollow conductive cylinder. The total charge inside the Gaussian surface is equal to the total charge on the hollow conductive cylinder. Since the charge distribution is a area charge distribution, since they have given the area charge density and since we know the radius of the hollow conduction is capital R and length of the hollow conductor cylinder, let's say simple L, given data radius capital R, radius capital R ne, radius capital R, radius capital R, okay, radius capital R, radius capital R, and radius capital R, okay, right. In this case, what we can do here, okay, here, right, here what you can do here, right, give me 1 second. Now here what you can do here, now, right, now, shall I consider like this? I consider this cylinder is somewhat large, look here. Okay, I'm doing a kind of small change here. I'm doing a small change. I'm going to increase the length of the cylinder. That's it, huh? Nothing else. We can do in this way also, but it's okay, we'll do in this way. I'm going to increase the length of the cylinder. This side also, I'm going to increase the length of the cylinder. Right. So then, the radius of the cylinder is same as R2. Sorry, capital R. Capital R. Now, what I was doing actually, I was finding the electric field intensity at point capital B. I selected a Gaussian surface, red color, cylindrical Gaussian surface. Its radius is going to be capital R. Radius of red color Gaussian surface is capital R. Let's say the height of the red color Gaussian cylinder is L2 something. L2. Right. Now we'll find the total charge. We know that area charge density sigma equals total charge over total area. I know the area charge density, that is sigma. What is the, now my target is to find the total charge inside the Gaussian cylinder. My target is to find the total charge inside the Gaussian cylinder. What is the charge covered by the Gaussian cylinder? Red color, think red color. Now forget about this blue color story. Now you want to think the black color cylinder and you want to think about this red color Gaussian surface. Black color cylinder and red color Gaussian cylinder. Think black color hollow conductive cylinder and red color Gaussian cylinder. That's it. That's it. So what is the total charge inside this red color Gaussian cylinder? If not, what is the charge covered by this red color Gaussian cylinder? That is going to be equal to sigma into area covered by the red color Gaussian cylinder. Right? Am I correct? Because, see, this idea. Because see, this is your cylinder. Right? It's a cylinder. Listen very carefully. For the through the entire surface of the cylinder, the total surface area of the cylinder is charged by positive charges. Right? Now your target is to find the charges inside this red color Gaussian cylinder. Charges inside the red color Gaussian cylinder. That means you want to find the charges on the cylinder, charges on the conductor, charges on the conductive cylinder covered by the red color Gaussian cylinder. If you want to find the total charge inside the Gaussian cylinder means the charges on the cylinder which is covered by the red color Gaussian cylinder. That means this charge. You want to find the total charge on this area. You want to find the total charge on this area. How do you find that area? If you know the Gaussian length is, let's say, Gaussian length is L2, the radius is the radius, Gaussian is L2, the radius is how much? The radius of the hollow cylinder, the radius of the hollow cylinder is capital R. What is the equation then? The equation going to be, right, surface area of the cylinder going to be, right, sigma into 2 pi radius capital R, length is L2. Hands up how the way I obtain this equation. Total charge inside the red color Gaussian cylinder is this one. Hands up, this story clear, hands up. 2 pi R L2, hands up. Did you understand how the way I got this? Clear? No issues? Just tell me. If you have a doubt, ask. Is it clear? No issues, right? What you want to find is just hands up once again. Hands up, please, quickly. Hands up once again. Didn't understand, hands up. If you have a doubt, ask. Why you? If you have a doubt, ask. Hands up, didn't understand, hands up, didn't understand. Didn't understand, hands up. Understood, hands up. Understood, hands up. Understood. Right? Okay. Then this is the total charge. Then apply the equation. If I apply the equation, intensity into area must be equal to total charge over epsilon. Right. Intensity capital E into the Gaussian surface area. Gaussian surface area. Capital A means Gaussian surface area. That is how much? Gaussian surface area going to be how much? 2 pi capital R. Gaussian surface length is L2. 2 pi R L2. 2 pi R L2. 2 pi capital R length is L2. The total charge inside the red color Gaussian cylinder, Gaussian surface going to be sigma into 2 pi capital R L2. 2 pi capital R L2 over permittivity epsilon. Then here 2 pi capital R L2, 2 pi capital R L2 cancel out. We are getting intensity as sigma over epsilon. Epsilon. Right. Right. Then I found the intensity at any point inside the cylinder, that is 0. If I find the intensity at a point just outside the cylinder, that is equal to sigma over epsilon. Let's find the intensity at a point which is far from the cylinder. Intensity at a point which is far from the cylinder. Right? Again, I'm drawing a Gaussian now. I want to find the intensity at point capital C. I want to find the intensity at point capital C. Point capital C. Again, draw a Gaussian cylinder. If I draw a Gaussian cylinder, if I draw a Gaussian cylinder, right? If I draw a Gaussian cylinder like this. So I draw that part separately in here to understand the diagram clearly. If I do that part here, if I do that part, this part, this is your cylinder. Cylinder radius how much? R. Cylinder radius R. And this time the point I want to find the intensity is far from, is outside the hollow conductor cylinder, is outside. My point capital C is somewhere here. Is my point capital C. It's my point capital C. Then if I draw my Gaussian surface, I'm drawing my Gaussian surface, another cylindrical Gaussian surface. Another cylindrical Gaussian surface. Right. Normally we use dotted lines to represent Gaussian surfaces. We don't draw dark colors. The Gaussian cylinder, right? I do the charges on the hollow conductor cylinder using my red color. The charges on the hollow conductor cylinder, the charges. The charges on the hollow conductor cylinder, the charges. The charges. The charges on the hollow conductor cylinder. Right. Okay. Length of the Gaussian cylinder is, let's say, L2. Length of my Gaussian cylinder is, let's say, L2. It's L3. And this is L3. And the radius of the Gaussian cylinder, let's say it as R3. Radius of the Gaussian cylinder is R3. 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 Where is my point capital C? My point capital C is R3 distance far from the center of the hollow conductor cylinder. The distance to point capital C, is simple R, capital R3 distance far from the axis of the conductive cylinder. Okay? Right. It's okay. It's okay. Right. It's okay. Right? If you want to color, I know coloring roughly. Is our Gaussian surface. Now shall we find the intensity at a point outside the hollow conductive cylinder? At point capital C. First of all, shall we find the total charge inside the Gaussian cylinder, blue color Gaussian surface. Blue color Gaussian cylinder total charge. Then total charge inside the blue color Gaussian surface. We know the area charge density is sigma. The area covered by the blue color surface going to be, right? The area covered by the, if I do the cylinder, see, if I do the black color cylinder, hollow conductor cylinder, the area covered by blue color Gaussian surface going to be this much. Correct me? The area covered by the blue color Gaussian cylinder going to be this much. Distance we know that is L3. And the radius, some people do a mistake. Remember, I want to find the total area. I want to find the total charge. We know the charge is on the black color conductor cylinder. So therefore, I know the length. Now, very simple. This is your black color conductor cylinder. The radius of the black color conductor cylinder is they have given as capital R. The radius capital R. Okay. What's my target? My target is to find the total charge on the black color conductor cylinder in an area covered by blue color Gaussian surface. I want to find the charge on the black color conductive cylinder in the area, only in the area covered by blue color Gaussian surface. Only in the area covered by blue color Gaussian surface. The charge on the black color cylinder only in the area covered by blue color Gaussian surface. That means I want to find only these charges. I only want to find these charges, right? Not entire charge. Then the equation going to be, right? The equation is area charge density sigma equals Q over area. Then my Q going to be how much? Sigma into area on the black color cylinder. Area on the black color cylinder means what? Sigma into area on the black color cylinder means radius R, length is L3, 2 pi capital R, 2 pi capital R, length is L3. Is the total charge on the black color cylinder. Total charge on the hollow conductor cylinder covered only in the area covered by the Gaussian surface. Right. Hence the story is clear answer. The way how I obtain this total charge answer. The way how I obtain the total charge answer. The way how I obtain the total charge answer. Total charge. This story is clear, right? Clear, right? Then we can write the equation intensity into area must be going to be equal to Q over epsilon. I want to find intensity, capital E. Area going to be how much? Area going to be the remember here in this equation, area means always Gaussian surface area. Remember in this equation, capital E means Gaussian surface area. How do I find the blue color Gaussian surface area? Radius R3, distance to point C is R3 from the center of the cylinder, R3, then 2 pi R3 into L3. 2 pi R3 into L3. 2 pi R3 into L3 must be equal to total charge. Total charge going to be sigma into 2 pi capital R simple L3. 2 pi capital R simple L3. Then here 2 pi cancel out. L3 cancel out. Finally, we can write down intensity means what? Oh, epsilon. So I forgot to write the epsilon. Finally, intensity means sigma capital R over sigma capital R epsilon, sigma capital R epsilon dot R3. If I'm wrong, tell me. Dot R3 must be equal to the intensity. Remember in this equation, sigma is a constant, epsilon is a constant, and the radius of the hollow conductor cylinder, unless you change a different cylinder, the radius of the hollow conductor cylinder going to be constant. So then remember here, intensity varies with the distance. What is the relationship between intensity at a point outside the cylinder and the distance? Relationship between intensity at a point outside the cylinder and the distance going to be a kind of inverse relationship. They are having kind of inverse relationship. When the point is far from the cylinder, your intensity is going to be very lesser. Is the idea. This idea. Now then, so then I think we found the intensity at a point inside the cylinder, intensity at a point on just outside the cylinder, intensity at a point outside the cylinder. Right? Based on this, shall we draw the graph? Variation of intensity with the distance. The variation of intensity with the distance. Draw graph. Shall we draw it? If we draw the variation of intensity with the distance. For the graph, how would be the graph? How would be the graph? If you do the graph, how would be the graph? If I do the graph. Again, we'll consider now when I draw the diagram, we'll consider the side view of the cylinder and we'll do the graph. If you're looking at the cylinder from the side, then how would your cylinder appear? I'm going to draw in here. Right. I draw a bit large cylinder. Center is the side view of the hollow conductor cylinder. I don't know, some people with the understand or not, I have no idea. If you have a doubt, you can ask. If you have a doubt, you can ask. the charges distribute on the outer surface of this hollow conductor cylinder. Outer surface of this hollow conductor cylinder. Outer surface of hollow conductor cylinder. Outer surface of hollow conductor cylinder. Right? Okay. Then if I draw the electric field lines, this is how it appears. But I'm not drawing the electric field lines. But if you want, you can draw the electric field lines also. I'm going to consider the variation of electric field intensity along this horizontal line. So this is your cylinder, hollow conductor cylinder. If I look from this side, this is how your cylinder look like. Your cylinder is going to look like a kind of a circle. If you're looking from this side, your cylinder is going to be a kind of circle. That's what I have drawn here. If I draw the variation of intensity, if I draw the variation of intensity with the distance, y-axis is going to be intensity, and your x-axis is going to be distance, and your x-axis is going to be distance. Just do the graph then. Idea is very simple. Now you know the idea. Now we know that when you consider any point inside the hollow conductor cylinder, intensity is zero. Intensity is going to be zero. And in if I draw the intensities, same story. If you consider few points, the variation of intensity. When you consider a point just outside the cylinder, if you mark the intensities, this point is point capital A for an example. Now according this diagram, point capital is somewhere inside. Point capital B is here, point capital C, point capital D, point capital D. If you mark the direction of intensities, I'm not going to explain that. A direction of intensity going to be right side direction. According to this equation, intensity proportional to the distance from intensity inversely proportional to the distance measured from the center of the axis. Right? Then as you go far, intensity decreases. Arrow size smaller. Right? The opposite direction also same story. Same story. Right? Then the graph going to be this side, right side direction intensities are measured as positive intensities. Left side direction intensities are measured as negative intensities. If you know the graphs, this is how they vary. This is how they vary. This is how they vary. Right? Okay. Next one also done. Done. The next one. Next one, write down around isolated, charged. Next one, write down around isolated, charged. Around isolated, charged. We are going to finish it. Around isolated, charged. Infinitely long, non-conductive cell cylinder. Around isolated, charged. Infinitely long, non-conductive solid cylinder. Non-conductive solid cylinder. Now it's non-conductive. Remember, if it is non-conductive, when you give a charge, if it is non-conductive, when you give a charge, those charge can store inside the cylinder as well. If it is a conductor cylinder only, the charge that we are providing won't store inside cylinder. If it is a conductor cylinder, all charges will store on the outer surface of the cylinder. If it is non-conductive cylinder, the charge that you are providing are distributing inside the cylinder through entire volume of the cylinder. Right? Then do the story. Then how would be the story? The next story. Next story. Will those touch x-axis? No, right? When r reaches infinity. Remember, this graph at y-axis it's touching, but x-axis it doesn't touch because why? We know that when r is infinity only, intensity will become zero. Therefore, these won't touch in your x-axis, but this will touch your y-axis. Right now, okay. Now, okay, right? Will touch in y-axis. So you can write like this. You can draw like this. The next story. Next story. Okay. Next one. Around isolated, charged, infinitely long, non-conductive solid cylinder. Right. We'll draw it. If I to the cylinder. Right. Cylinder. Fine, right? This is a non-conductive solid cylinder. The axis. Then shall we, let's say now charge is distributed inside the entire volume of this non-conductive solid cylinder throughout the volume. Then quickly find the intensity at a point inside cylinder, intensity at a point just outside cylinder, intensity at a point outside the cylinder. Then when you draw it, how would be the diagram? Right. Again, given data. Let's say they have given in the question they have given volume charge density given. It's obviously we understand that the charge distribution going to be a volume charge distribution. And when you draw the electric field lines, you know how would the electric field lines look like. Just draw the side view and just draw the front view and try to draw the how the way these electric field lines distribute on this non-conductive solid cylinder. Just draw the electric field line distribution considering side view and the front view. Just draw it. Just draw it quickly. Just draw it quickly. Just draw it quickly. Draw it. Draw it quickly. Yes. And they have given volume charge distribution is rho and volume charge distribution is rho and the radius of the non-conductive solid cylinder is capital R. Radius capital R. Volume charge distribution is rho. Radius capital R. Okay, right. Then if I want to find intensity at a point inside the cylinder through a Gaussian surface. If you draw a Gaussian surface, let's say I want to find the intensity at a point capital A somewhere here. Point capital A somewhere here. Draw a Gaussian surface perpendicular to electric field lines, and this point must be on the Gaussian surface. Then when you draw a Gaussian surface, that is going to be a kind of cylindrical Gaussian surface. That is going to be a kind of cylindrical Gaussian surface. Okay, ne? Point capital A. And the radius of the Gaussian cylinder, radius of the Gaussian cylinder, that is, let's say, R1. Length of the Gaussian cylinder, let's take it as L1, R1, L1. Then, yeah, step number one is identify the charge distribution, that is going to be volume charge distribution. Step number two is identify the electric field line distribution. Already you know that, but I do the diagram. How these electric field lines distribute? If it is side, if you do that, now I'm not drawing the electric field lines on this main diagram, but same diagram I draw a smaller scale and I show how the way electric field lines distribute when you look from front. The front view going to be the front view. If I draw the electric field lines, this is the axis passing through the axis of the cylinder. It's the axis. And if I draw these electric field lines, since charges are spread throughout its volume of the non-conductive solid cylinder, electric field lines is non-conductive. Electric field lines are starting from inside of the cylinder. Electric field lines. This is the front view. Charges. And when you draw the side view, someone is looking from the side view of this diagram going to be look like? The side view going to be look like? The side view. The side view, now so when you look from the side, you don't see this as a cylinder. You see it as a kind of circle. Then when you draw the electric field lines, they distribute from the center of the cylinder. Electric field line distribution. Right? The front view ends at the side view. Now, shall we find the electric field intensity at point capital E? Then we want to find the total charge inside the Gaussian cylinder. Total charge inside the Gaussian cylinder. Given data, they have given that volume charge inside is rho. We know this equation. We know that uh, volume charge density equals the total charge over the length, total charge over the volume. If you want to find the total charge inside the red color Gaussian surface, red color Gaussian cylinder, let's say total charge inside the red color Gaussian surface, red color Gauss cylinder, let's take it as Q1 something. Q1 going to be equal to rho into the volume of the Gaussian cylinder. What is the volume of the Gauss cylinder? If you want to find the total charge inside the Gauss cylinder, you should find this volume. Am I correct? You should find this volume. This volume going to be equal to how much? Radius is R1, length is L1. Cylinder volume means we know that pi r squared into h. Cylinder volume equation is pi r squared into h. Then pi R1 squared. The height is L1. Okay, that's it, right? Okay, this is the total charge inside the Gaussian cylinder. And now we can apply the equation. If you apply the equation, intensity into area, must be going to be equal to Q over epsilon. Then you want to find the intensity at point capital A, EA whatever, EA into this area going to be, area means Gaussian surface area, that is equal to cylindrical area. Equation is 2 pi R1 L1. 2 pi R1 L1. 2 pi R1 L1 must be equal to total charge going to be rho into pi R1 squared L1. Here this pi and pi cancel out. R1 cancel out. So what we can write down here is, intensity at point capital A going to be equal to, how much? That is going to be equal to rho R1 L1. Okay, I can cancel out L1 also. Then rho R1 over, I forgot to put the epsilon also. 2 epsilon. Am I correct? Rho R1 over 2 epsilon. If I'm wrong, tell me. So remember here, rho is a constant. Epsilon is a constant. Right? When you consider different points inside the non-conductive cylinder, your R1 changes. When R1 changes, the distance inside the cylinder changes, your intensity at that point also changes. The relationship between intensity inside the cylinder and the distance is what? Inversely proportional, directly proportional to R1. This story. This is point capital A. Shall we find the intensity at a point just outside? Intensity at a point just outside the Gaussian cylinder. Just outside. In this case, if my Gaussian surface is going to be just outside my Gaussian surface, this is my Gaussian surface. My Gaussian surface, right? The point going to be point capital B. This point is going to be point capital B. This point is going to be point capital B. The radius of the this red color, I say Gauss. This is second red color one. Radius of the second red color Gauss surface. Let's say this radius is going to be, let's say, capital R, because I'm going to consider intensity just outside the cylinder. So this red color Gaussian cylinder radius is going to be same as capital R. Same as capital R. You should not use dotted lines. You should use dotted lines. To represent a Gaussian surface, we are using dotted lines. And the length of this is going to be, let's say, L2. 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 Now in this case, if I want to find the intensity, first of all, I want to find the total charge covered by the Gaussian surface. This one, right? Look here. Then in that case, see the idea. The same story. Same story. This is your black color cylinder. This is your black color cylinder. And then this is that red color Gaussian surface. If I do the red color Gaussian surface, this is going to be the red color Gaussian surface. This is going to be the red color Gaussian surface. Okay. And if you want to find the charge inside the red color Gaussian surface, you want to find this volume. Am I correct? So you want to find this volume, the volume covered by the red color Gaussian surface on this black color conductor. Then the radius is going to be same as R. Radius is same as R. Radius is R. And this height going to be L2. Then the volume covered by the red color Gaussian surface on this non-conductive cylinder is pi r squared into L2. Pi r squared into L2. Right. In that case, again, if you find this equation at point capital B, the equation, volume charge density must be equal to total charge over total volume. Total charge over total volume. Let's say the charge inside the red color Gaussian surface is going to be Q2 something. QB something. QB must be equal to rho into that blue color volume. Rho into blue color volume is how much? Blue color volume is pi capital R squared. Pi capital R squared L2. Now you can apply the equation. When you apply the equation, intensity into area. Intensity into area must be going to be equal to how much? Must be going to be equal to capital Q over epsilon. Intensity at point capital B, EB. EB going to be equal to total area going to be how much? Total area, Gaussian surface area. Total Gaussian red color area. This is red color area. Pi capital R squared L2 must be equal to rho into pi capital R squared L2 over epsilon. I think pi capital R squared L2 cancel out. Then we are getting rho over epsilon something. As EB. As EB. It's a constant. So when you substitute EB means rho over epsilon. Likewise at point capital C. If you take point capital C, just take point capital C. When you consider point capital C, look at your point capital C. At C. At C. Again, you want to select your Gaussian surface. Where is the point C? Point C is far from the non-conductive cylinder. Point C is far from non-conductive cylinder. Select a Gaussian surface. This time my Gaussian surface is going to be something like this. This time my Gaussian surface. My Gaussian surface. Right? I draw here. The radius is capital R. This time it's a volume charge distribution. In that case, since it's a volume charge distribution, right? I am interested on charges. I am interested on the charges covered by this blue color Gaussian surface. Point capital C is R3 distance far from center of the cylinder. Is the same story. Same story. Find the total charge inside the Gaussian cylinder. At point C, the total charge inside the Gaussian cylinder. The total charge inside the Gaussian cylinder. Find the total charge. The total charge. Sigma equals Q over volume. That means Q3, let's say Q3 something, QC. Sigma into this volume. This volume going to be pi, right? Pi R squared, pi capital R squared. So you want to find the volume of the cylinder with covered by the Gaussian surface. Pi capital R squared into L3. Same story. Then here area means Gaussian surface area. Blue color Gaussian surface area going to be how much? Phi R3 squared. Phi capital R3 or simple R3. Phi simple R3 squared. Pi simple R3 squared into the height is L3. Must be equal to sigma into pi R squared L3. Very simple. Pi R squared L3 over silent. Pi cancel out. Then when you simplify it, L3 cancel out. When you subtract, intensity equals sigma into R squared over epsilon R3 squared. Then you understand your intensity going to be proportional to 1 over R3 squared. That's it. So when you plot the graph, see, remember, when you plot the graph, the difference is what? The difference is going to be what? Just think what the difference. Inside the cylinder C, look here, intensity is directly proportional to the distance measured from the center of the axis. Remember, when you consider any point inside the cylinder, the intensity is proportional to the distance measured from the center axis. When you draw the graph, this is what you get. This is what you get. Right. Done. Difficult stories are done. Everything is very clear and up now. Up now, everything is very clear and up to now, everything is very clear and now that's it. If you can understand the story, it's not going to be difficult. You will able to understand everything. So then that is also discussed, and now how many examples more to go? And so we have 2 more examples, I think. Finished, hands up. Finished, hands up. The next one, write down. Next example. Around isolated charged. Around isolated charged. Around isolated charged. Conductive. Conductive. Infinitely long flat plate. Infinitely long flat plate. Infinitely long flat plate. Right. How we do this? How we find intensity at a point? If the charge distribution, the charge is distributed on the surface of flat plate. If the charge is distributed on the surface of the flat plate, how are we going to find the intensity at a point simple r distance far from that? Far from that. How can we do this? How can we do this? How can we do this? Right. In this case, okay. In this case, right. In this case, right. Look here. If I do the diagram, I erase this entire stories. If I erase the entire stories, now there is a conductive plate. Remember, it's infinitely long. What have they given in the question? Around isolated, charged, conductive, infinitely long flat plate. What they are coming to tell is they are telling that the surface area of the flat plate is infinite. It's a very long, infinitely long flat plate. Let's say when you apply some charges, when you supply charges to that flat plate, remember that charge is going to store. When you consider a very thin flat plate, how many surfaces are there? Raise your hands. How many we see? If there is a flat plate, how many surfaces are there on the flat plate? In the flat plate, how many surfaces are there in the flat plate? Hands up. How many we see? There is only one surface. Hands up. When you consider a flat plate, there is only one surface. Hands up. So there are two surfaces, this side and the opposite side. Hands up. Obviously, if there is a flat plate, there are two surfaces. Then when you supply, let's say, capital Q amount of charge to the flat plate, that capital Q amount of charge going to store on both the sides of the plate, right? If I say that that capital Q charge that you supply to the flat plate evenly distributed on both the plates, what is the charge stores on one side of the plate? Or what is the charge stored on one side of the plate? Obviously Q by 2. Obviously Q by 2. You are supplying capital Q amount of charge. You are supplying capital Q amount of charge. We know that charge going to be stored on both sides of the plate, let's say evenly. In that case, if this side also going to charge, if the opposite side of the plate also going to charge, means the charge storing on one side of the plate going to be obviously Q out. Right? That story keep in your mind. That story keep in your mind. Right? That story keep in your mind. Right? This diagram. So what you can do, you can draw a kind of a 3D flat plate. Then I will draw the 2D story also. So when you are deriving, okay, right, right. In this case, right, your flat plate. The flat plate. And when you supply charge, that charge going to store on both sides of the plates. I only consider one side. I'm not showing what happened to the other side. I draw only one side of the plate. Then we can see that, let's say positive charges are stored on the one side of the plate. The charges are storing on both sides of the plates, but I only show you. I'm only drawing considering one side of the plate. I'm only drawing the one side of the plate. Right. The charges. What's my target? I want to find the distance. If I measure, if I consider a point which is perpendicular to which is perpendicular to simple r distance far from the plate. That's a point. I want to find the intensity at that point. At that point is simple r distance far from the plate. In that case, how I'm going to find the intensity at this point? I name this point as point capital E. My target is finding the electric field intensity at point capital E. How can I find this? How can I find this? Now again, you want to apply same law. You want to follow 5 steps. Find the charge distribution. Anyone can understand that is a kind of area charge distribution. Then try to find the electric field line distribution. Then select a suitable Gaussian surface. Find the total charge inside the Gaussian surface. Apply the equation. Same story for this story also. But remember now you can get the intensity at point capital A by following 2 different methods. One can consider only one side of the plate and one can find the intensity at this point. If one can consider both sides of the plate and one can find the intensity at this point. I will explain you, don't worry. I will explain you, don't worry. Right. In this case, now what would be the shape of your Gaussian surface? Any idea? Let's say how many of you can answer this story? Let's say how many of you can answer my question? What can you say about the Gaussian surface? What would be the shape of your Gaussian surface? We know that. Just imagine, first of all, imagine how would be your electric field lines leaving from that flat plate. Just imagine, just consider one side and that side is positively charged. Just imagine how would be the electric field lines leaving from that positively charged flat plate. If you imagine the electric field lines, then your Gaussian surface must be a perpendicular surface. Your Gaussian surface must be perpendicular to electric field lines passing through that Gaussian surface. Now my question is, what would be the shape of the Gaussian surface that you want to select? Any ideas? Give some your ideas, give some your opinions. What would be the shape of your Gaussian surface? What do you think? The requirement is this point capital A must be on the Gaussian surface. The second requirement must be the Gaussian surface must be perpendicular to the electric field lines passing through your Gaussian surface. Just put some replies. What would be the shape of your Gaussian surface? What would be the shape of your Gaussian surface? Put some replies. Put some replies. Put some replies. One is telling rectangular square. Other one is telling cylindrical. That's wrong. One is telling rectangular square. Other one is telling cylindrical. That's wrong. Cylindrical. That's wrong. Right? If you say cylindrical, that's wrong. Because the Gaussian surface must be perpendicular to the electric field lines. Just imagine how would electric field lines leave from this positively charged flat plate. I draw somewhere here because if I draw in this main diagram, everything will be very messy. I'm drawing the electric field lines, I'm drawing the Gaussian surface, I'm defining the variables, then the diagram look like very uncomfortable, very what messy. Therefore, if I draw that diagram again for your understanding, first you want to understand how your electric field lines propagate from the Gaussian, propagate from this plate, propagating on this plate. Okay, propagating from this plate. Electric field lines leaving from the plate perpendicular to the plate. Electric field lines leaving from the plate perpendicular to the plate. If I draw some perpendicular electric field lines, perpendicular electric field lines, some perpendicular electric field lines. This is not the line, okay? Don't misunderstand. If I draw some perpendicular electric field lines, shall I use red color? If I use red color, perpendicular electric field lines, use red color. The electric field lines perpendicular. Perpendicular electric field lines. Want to draw, there are many electric field lines, but I'm not sure if I draw all the electric field lines, this diagram will be very messy. I try to draw another layer. Electric field lines. Perpendicular electric field lines. Perpendicular electric field lines. Perpendicular. Right? Now, do I want to draw the remaining electric field lines? I think I don't need to draw the electric field lines remaining, right? Because this is more than enough to understand what's happening here. If I draw a set of electric field lines at the bottom, if I draw another electric field lines at the bottom, perpendicular electric field lines. Okay. Perpendicular electric field lines. Right. So then this story is very clear now. Then, sir, remember, you should select an area. You should select an area. That area must be perpendicular to this electric field lines. Just think this is your plate. Just think this is your plate. This is your plate. This is your plate. Now just think these are the electric field lines coming, leaving from the plate, perpendicular, leaving from the plate, leaving from the plate, to the plate. Okay? Electric field lines. It doesn't matter. You select a rectangular area O. You select a circular area O. You select a triangular area O perpendicular to the electric field lines. Anyhow, circular area, rectangular area, triangular area, whatever, going to be perpendicular to the electric field lines. Right? It doesn't matter you select a circular area. Doesn't matter you select a rectangular area. If you select a triangular area, remember, they are always perpendicular to electric field lines. Answer, the story is clear answer. The story is clear answer what I'm saying. I don't know how many of you understand. Right? Therefore, it can be any shape in this scenario. For the previous cases, we can't select any shape. But in this scenario, it can be any shape. It can be any shape. It can be any shape. I'll try to just justify, let's see, by drawing some diagrams, whether we can prove this. Right in here, at point capital A. Try to understand, not sure you will understand or not. This is the area perpendicular, see. This is point A, see, this is the area perpendicular to, this is the area passing through point capital A, perpendicular to electric field lines. Right, see, this is the area. So this is the area. This is the area, right? This is the area perpendicular to electric field lines passing through this area. So you can select any area, any shape on this plane, right? On this plane, you can select a circular area. The circular area is going to be perpendicular to electric field lines. This point capital A is exactly on this area. You can select a rectangular area. You can select a triangular area, doesn't matter. They all are in the, they all are perpendicular to the electric field lines. Generally, hands up that idea, clear answer. That idea is clear answer. That idea is clear answer. Then that's it. Then that's it. You can select a rectangular area. You can select a triangular area. Whatever. It's up to you. It's up to you. It's up to you. I select a circular area. You can select any area. It's up to you. If I select a circular area. If I select a circular area. This is my circular area. Okay. This circular area, let's take it as delta E. Circular area delta E. Now we'll do the side view. If you do the side view, look here, the side view. This is your plate. flat plate, and perpendicular to the flat plate at a distance simple r. Your point capital E. Your point capital E is here. This red color area is perpendicular to electric field lines. This red color area going to be delta E. This red color area is going to be delta E. Delta E. Right? Right. Then find the answer. Given they have given, let's say now they have given area charge density given as sigma. Remember, they have given area charge density, they have given as sigma. Area charge density, they have given as sigma. Sigma. Right? Find the answer. Sigma. Find the answer. Find the answer. So then, if I do the electric field lines, remember the plate is your plate, is your thin plate. It's a conductive plate. So therefore no charges inside the plate. All charges are storing on the outside surface of the plate in the both the sides. All charges are storing on the outside surface of the plate. That means both the sides. That means both sides. Right? Shall we do some electric field lines? If I do the electric field lines like this, the electric field lines are this direction. Correct, right? Electric field lines. The electric field lines. The electric field lines. And the electric field lines. If I do the electric field lines this direction, electric field lines, electric field lines, electric field lines, field lines, right? Okay. Okay. So the step 1, step 2 clear, step 3 select a Gaussian surface. This time I consider a circular Gaussian surface. This time circular Gaussian surface. My Gaussian surface is circular. My Gaussian surface is circular. Now I am just marking like this. You don't misunderstand. The Gaussian surface is kind of a cylindrical one. Don't misunderstand. I want to show this cylindrical shape to tell that only this part of charge, the charges in this region only going to contribute for the intensity at point capital A. Right? Actually, Gaussian surface is a circular area, not the cylindrical area. Don't misunderstand that. I explained here properly. But why I am drawing a cylinder is to show that only this part of the charges only in this region going to contribute for the intensity at point capital E. That's my target. Right? Then what you can do, the total charge. Right? So the if then only okay, the charges belongs to see the cylindrical part. The charges belong to this circular area on the flat plate. The charges belong to circular area delta A on the flat plate going to contribute for the intensity. Going to contribute for the intensity. Going to contribute for the intensity. Right? Then you can tell that your sigma total charge inside the Gaussian surface going to be sigma q going to be just they have given the area charge density is sigma into what the area is delta E. Only this area. The charge is only in this area. Charge is only in this area. That is delta E. Delta E. When you apply the equation, intensity into area must be equal to sigma, sorry, Q over epsilon. Q over epsilon intensity. Area is, this is your delta A. Delta A must be equal to sigma into delta A over epsilon. Delta A cancel out. Intensity going to be equal to sigma or epsilon. That is one way. Sometimes what we do, some people what they do. Now here I considered only the electric field lines. I considered only one side of the electric field line distribution, one side of the charge distribution, and based on that only I found the intensity at point capital A. But what some people do, what they do, they consider both sides. That is not important. Finish writing answer. If you finished writing answer, now almost finished, done, almost finished, almost finished. Finish writing this, just raise your hands. If you finish writing, raise your hands. Right. The some people what they do, now. That's not important. If this is your flat, it's okay. Write down considering both sides. If you consider only one side, this is considering only one side. If you consider both sides, it's a flat plate. The charges. If I draw the electric field lines, but remember, electric field lines can't pass through the conductive plates. We know that story. We know electric field lines can't pass through the conductive plates. That story we know. Electric field lines can't pass through conductive plates. We know. Can't pass. Some people, what they do now, they consider now this entire electric field line distribution from the plate, and again Gaussian surface is going to be a circular area, but I am drawing here a cylindrical thing, but you don't misunderstand. Gaussian area is not a cylindrical one. Gaussian area is going to be a circular area. This time they are considering this area delta A, this area also going to be delta A. If you consider electric field line distribution happening in both sides of the plate, right? The total area through which electric field lines propagate, right? If you consider both sides, the total area through which electric field lines propagate is delta A plus delta A to delta A. Total area is to delta A. Total area is to delta A. If you want to find the right, then you want to understand charges storing in this side of the plate as well as charges stores on the left side of the plate also. If you want to find the total charge, what you want to do is, we know that sigma equals q over area. If you want to find the total charge equal to sigma into the total area, delta A plus delta A, delta A plus delta A to delta A, to delta A, right? Then you can write the equation intensity into area must be equal to what? Charge over epsilon, intensity into these electric field lines are propagating in both the areas. Right, these electric field lines are propagating through both the areas. The total area through which electric field lines propagating is delta A plus delta A to delta A must be equal to total charge is sigma into 2 delta A over epsilon. Again, you are ending with intensity equals what? Sigma over epsilon only. Same story. MCQs, they are asking these stories. I think now you understand these ideas and all. And the last one, then finished. One last one, then finished. Then finished. Now we can talk about electric potential and stories. Electrical potential energy. Then today we are drawing some graph stories. Okay. Right. Okay. Right. Okay. We'll take a small break after doing this. The last one. Write down. around charged, isolated, infinitely long, non-conductive plate. Around charged, isolated, infinitely long, non-conductive plate. Around charged, isolated, infinitely long, non-conductive plate. Now here, if it's non-conductive plate, we know that charges won't store on the surface of the plate. Charges store inside the plate. If it's non-conductive, like the conductive plate, here in the conductive plate, charges store on both surfaces of the plate. Both the outer surface of the plate. Charge, if it is a conductive plate, charges stores on both the outer surfaces of the plate. But if it is non-conductive, charges they won't store on the outer surface of the plate, charges store inside the plate. If it is non-conductive, charges store inside the plate. Inside the plate. Right? Same story. Same story. Same story. Charges storing inside the plate. I don't like this. Electric field lines passing in both directions. Still. Right? So if I do a side view, see, they have given this time, they have given what? They have given this time, they have given, this time they have given, they have given again, since it's a thin plate. Remember, now, if charges are storing inside the plate, normally that charge distribution must be a kind of volume charge distribution. That's how we consider in the previous stories. But remember, since they mentioned this plate is very thin, we have to consider charges are storing inside the plate only, not the outer surface of the plate. Since the plate is very thin, we have to consider the charge distribution as kind of area charge distribution. If the plate has a considerable thickness, then definitely you want to consider charge distribution as a volume charge distribution. Since the plate is very thin, you have to consider the charge distribution as a area charge distribution. Right? This is your plate. Charges are inside the plate. Right? And in this case, we know that electric field lines pass in both directions. Right? Electric field lines can pass through the plate. Why it's non-conductive? Electric field lines can pass through the plate. Why non-conductive? Why non-conductive? Again, your Gaussian surface. You want to find the intensity at a point, simple r distance perpendicular to the plate, far from the plate. You want to find the intensity at a point, simple r distance far from the plate, perpendicular to the plate. Simple r distance far from the plate, perpendicular to the plate. Simple r distance far from the plate, perpendicular to the plate. You have to target is to find the intensity at this point. Then as previous story, your surface area going to be a circular surface area. It can be rectangular shape also, doesn't matter. I considered your Gaussian surface as circular Gaussian surface. Since the electric field lines are propagating in both directions, I consider opposite direction also. Right. The only difference is, I will tell you. Shall we apply the Gaussian law? Okay, shall we apply the story? For this, they have given area charge density of the charge distribution is sigma. Then what's my target? This area delta A, radius simple r, delta A. Delta A. What I want to find? I want to find the intensity at this point. I want to find the intensity at point capital A. I want to find the intensity at point capital A. How can I find? I want to find the total charge inside your Gaussian area. Remember, now in the previous case, charges evenly distribute on both sides of the plate. For an example, if you consider this area on the right side surface of the plate, let's say the charge is plus 5 coulomb. Same area in the left side also, the charge stores on the left side also 5 coulombs. Therefore, altogether, total charge inside that region is 10 coulombs. But when it comes to non-conductive plates, If you want to find the charge inside this region, that is only going to be equal to one of the areas, right? You can't consider this area delta A, this area delta A. The total area is 2 delta A on the plate. Charge is distributed on both sides of the plate, and you can't multiply by 2 delta A like you have done previously. I said that charges are not distributing on the surface of the plate. Charge is storing only inside the plate. Only inside the plate. Charges are only inside the plate, right? So therefore, if you want to find the total charge inside this red color region, that is how much Q equals sigma into delta A, right? Then when you apply the equation, intensity into area must be equal to Q over epsilon. Intensity, now the area means, remember, the total area through which electric field lines belong to that charge. The total area perpendicular to the electric field lines, right? Remember, what is capital A? Capital A means what? Here capital A means Gaussian area. Gaussian area means, right, because of that this much of charge, remember, because of this much of charge, electric field lines are propagating not only in the right side, but also electric field lines propagating in the left side also. In that case, you want to find the total area perpendicular to all the electric field lines propagated due to this much of charge. Do you understand? Because of this amount of charge, electric field lines are propagating in both directions. Therefore, you want to find the total area through which all the electric field lines propagated. Therefore, the area is not 1 delta A, it's going to be 2 delta A. 2 delta A must be equal to sigma into delta A over epsilon. When you simplify this, intensity is going to be equal to how much? It's going to be equal to sigma over 2 epsilon. Done and dusted. Done story. Answer. The story is very clear answer. Everything is very clear answer. Everything is crystal clear answer. Everything is very clear answer. Everything is very clear. Right. So then the Gaussian theory, that's it. Gaussian theory, that's it. Right. Gaussian theory, that's it. Right. The Gaussian theory, that's it. Then what we can do? Then right. We'll take a small break and come and now you can do any question. Any Gaussian question you can try. You can try all the past papers. This knowledge is more than enough. You can try any question. What shall you do after the break? We'll do that electric potential stories also. So then we can take a small relax. We'll do this electric potential stories also. Just take a small break and come. Time is 9:30. Come at 9:45. Hmm, right. If not, we'll do this 10 p.m. We'll start that paper discussion. Now tomorrow we'll start that. Tomorrow also, tomorrow night also we'll discuss. Tomorrow we'll do this electric potential story, and there are some graphs. Intensity potential graphs are to be drawn. That story also will draw it. Right. Today 10 p.m. we'll discuss that final paper 2. We have 20 MCQs pending, and final paper 1 essay also we have 1 essay question and 3 structured. Today we'll plan that MCQ discussion complete. Okay, we'll stop the class for now, and 10 p.m. we'll start the discussion.